Okay, so I'm going to give a talk about how to improve utilization signals for EAS. So my name is Pierre and I'm working at ARM. So the motivation of this talk is that I started to review Vincent's patch to rework EAS to handle more cases. And EAS is based on utilization values, and these utilization values needs to be accurate to make good decision to place tasks on the right CPUs, and it led to some more in-depth study of utilization on that in general. So, yep. So I'm going to talk mainly about PELT in the first slide. So I assume that it has been presented many times before, but need to go through this again, I guess. Then the influence of co-scheduled tasks on the utilization average of one task. Then I'm going to present some kind of new signal to take this into account to remove the influence of co-scheduled task on the utilization of one task. And I'm going to give some workload example, talk briefly about the limitation of the utility average value, and present something, a smaller topic, so the PELT granularity. So PELT is so it stands for per entity load tracking. It's a way to estimate the size of a task or how busy a CPU is. It's based on a geometric series with a ratio of 0.5 and a half-life of 32 milliseconds. So it means that after okay. No, I can point out. Oh, so yeah. So it means that after 32 milliseconds, the contribution of a contribution will wait for half the initial value of the contribution. So this is that function. So in green, it's the continuous function. So the real function, let's say, and in blue, this is what is used currently in the kernel. So it's an approximation of the function. So it's a staircase approximation. And we get one approximation for every 1 millisecond. So, also skipping this slide. So here I'm going to present how we account these contributions. So on the right, so I didn't present this, but this is the scale of the PELT function. So you get a value between 1 and 0. The y-axis is representing the time in the past. So you start on the right, you go to the left, and here we are seeing the contribution which was 10 milliseconds in the past, 60 milliseconds in the past, and it goes like this. The maximal contribution that we can have is going to be the whole area of this graph. So if you run a task if you have a task which run 32 milliseconds, then sleep 32 milliseconds, the contribution are going to be accounted like this. So you can see that the more the contribution is in the past, the less it's going to wait in a signal. The red line here is representing each contribution at a given time. So here you have no contribution, so it doesn't increase the red value, the red signal. Here you are accounting the contribution, so it's the red line is growing, and the more you go in the past, the less it grows. And here we have the final value, which is scaled on a 1024 value. Yeah. So as I said, in green it's the contribution, in orange it's the maximal error that we can contribute, and the ratio between the two area is going to be the signal that we are monitoring or using. Yep. So I'm not going to talk about the load, but mainly about the running and the runnable values. So we are accounting a running contribution when the task is actually running. So here we have a green task and a blue task. So in red, it's the utility average, so the running value. We are accounting a contribution when the task is only running. So when the blue task is unqueued, meaning when the blue task is running, we are not accounting anything. And the renable signal is accounting the contribution when the task is unqueued on the CPU. So even if the blue task is running, we are still increasing the renable signal. So yeah, so interpretation. So if we have only one task on one CPU on the CPU, the renable and the running signal are going to be the same. If we have multiple tasks, the renable signal is going to be higher than the running the utility average. Then, so there is something else that we're keeping track of, which is utilization. So it was introduced to store another information. So if we have one task which is running during a long amount of time, then not running during so here 128 milliseconds, the util average value is going to slowly decrease. And when we are going to enqueue the task again, we forgot that the task was big when it was running. So we like to keep this information, and we are storing the util average when we are dequeuing the task in the util S signal. And we are, so when the util average is higher than the util S signal, we are replacing the util S value with this higher util average signal. Otherwise, every time the task is dequeued, we are slowly decaying the util S signal. So when we have multiple tasks on the same CPU, okay, so we have different cases where the util average is going to grow slower. So first, it's when you are running on a smaller CPU or on a CPU which is running at a lower frequency. And second case is that if we have multiple tasks on the same CPU, because we are going to have to share the run queue with another task, so we have less contribution, and the util average signal is going to grow slower. It's an issue because when we are dequeuing that task, the util S value is going to be slightly lower than if the task had been running alone on the CPU. So we are slightly higher, and when the task is unqueued alone, we could raise the OPP at a lower level than what we would have done if the task had been running alone. And so it's an issue for utilization mainly. So right now the approach is another phenomenon that can happen, that when we have a CPU, the CPU is always running, the other task can push the util average value down. So to prevent this, the current approach is that when we have a delta between the runable and the running util average value, when this delta is higher than a certain margin, we are not decaying the util S signal. And like that, we are still having a higher estimation of the task, but still it's not really the accurate estimation of the task. So it was done on dispatch, it's a bus effort implementation, because we don't have access to any other metric to do that. So util burst is it's a control prototype, hasn't been submitted yet. And the goal is to prevent this or find a solution for this. And actually, I think it was an open issue in the slides from Vincent. So yeah. So to do that, what we are doing is that we are accounting the running time between the NQ and DQ events, and we are going to account all this contribution at once instead of increasing the util average signal whenever the task is actually running. So to show that, so here we have a green task and a blue task. First, from the green task point of view, we are not running when the blue task is running. So it seems like we are actually it could be that the task is sleeping, but actually not. And second step is to just compact the contribution in one single contribution. Like this, you're going to have a util average slightly higher than what we are currently monitoring. So one example, so here we have one task which is running on the left part of the slide to a certain to 30% duty cycle. And on the left part here, it runs then at 20%, here at 45%. We are seeing util average and the renewable signal. They are the same because there is only one task. The util S signal is either increasing, which is not okay, or decaying when the task is running less. So it's perfect. When we have two tasks on the same CPU, if the duty cycle of the task is slightly increasing, the util S is able to grow, but due to the margin, we are not taking this. The margin, the util average and the renewable signal are higher, have a delta which is higher than the margin, so we are not decaying util S. So we are currently overestimating the task with the util S. And if so, here, so the util burst signal is in orange, and with this signal, we are slightly higher than the util average because the util average is prevented to grow because the other task is running at the same time. And so I reverted the patch with the margin to use util burst. And in both cases, we are either able to grow util S or to decay util S. And the util S is actually the same as in the first slide, so in the slide where the task was running alone. So this margin was introduced because in a certain benchmark, so speedometer, the main thread, which was a big thread, was running on a big CPU, and in some cases, the utilization of this thread was so low that the thread was migrated to a medium CPU, which was decreasing the performance. With this margin approach, so it solved the issue of having this main thread being migrated to the middle CPU. But the issue is that we are overestimating the task in a lot of cases. When I removed this patch, so it led to a decrease in performance, so minus 2.1%. But so in my opinion, it's also because we are overestimating the size of the task. So obviously, we are going to run at a higher frequency, and it's going to be better, but not necessarily for the good reason, I guess.
But what was the issue actually? Like when you discovered all of this, was it power or energy consumption, or was it just because the signal was weird?
It was mainly because the signal was weird, to be honest. From a power consumption, it actually doesn't increase the power consumption so much, and the performance is better. So it's
in this specific speedometer test case, or?
Yes, in this case. Yeah.
But I mean, the weird util S signal might have like a negative effect on workloads we are running when we are interested in power savings or energy savings, right?
Yeah.
That's why you want to.
Okay. But yeah, so Vincent also talked about the fact that using util S, it might put the CPU more often in the overutilized state, and it also might be a reason as well. So here I'm using util burst, so the graph looks a bit smoother, and you can see that the impact of the other task is actually it doesn't seem so important. And compared to the base.
Just for me there, so your util burst is following tightly the util average.
Yes.
So do you have this kind of potential in this use case? I mean,
Sorry,
because
doesn't
it
seem so.
just seemed like the ETLS.
Right. Another thing that I'm updating util burst only when we have been running more than 1 millisecond. Well, no, yeah, 1 millisecond actually. So in some cases we are not updating util burst. So it's not active all the time right now. It's only active when we have been running for a certain amount of time, so more than 1 millisecond.
No, my point is just that I was expecting your util burst to maintain the ETS at some high level because they were co-scheduling and the time should have been the same. But when I look at the goal was to remove some of the current ETLS. It's just to say, as long as we are not running alone, we don't decrease the ETLS. So we can probably have some. The ETLS stay high, whereas the utilization of the task, or the max utilization of the task is decreasing, but we are not able to see that. With your util burst, it looks like we are always. I was expecting that your util burst at some time stay high because the util average was decreasing while sharing the CPU with other tasks. But the maximum utilization should remain the same, but I don't see much place like that there. So yeah. I'm not sure I'm clear in my explanation.
So I'm going to try to answer. So in util burst, I'm resetting the value of util burst to the util average when we are unqueuing or dequeuing. I don't remember. And second thing is that I think it's also the fact that I'm not always using util burst because of the 1 millisecond thing. And third thing is that maybe actually this main thread is not co-scheduled that often. Meaning that most of the time the thread is able to run what it wants.
Yeah, but if it was not co-scheduled that often, we should have seen typically, if you look at the chart on the top right.
You mean here?
No, I mean on the top, this one. You see that there? It means that we have some co-schedule for a long time. But if we look at, it's not exactly the same, but I was expecting that at some point the utilS using util burst to still stay high because the task behavior has not changed, but it was co-scheduled. But I don't see that anywhere. My point? I'm not
sure. Yes.
The goal of your util burst is to remove the case where we are co-scheduled, but so we are co-scheduled. My point is that there are some cases where we are co-scheduled, but the running time remains the same. So we should still use the same. We should still end up with the same utilS. Right now, instead of trying to compute this value, we are just filtering the value. But your util burst, if I understood correctly how it works, the util burst should end up at the same value as long as the task is not changing its behavior.
Yes.
But I'm not seeing that there in your chart at the bottom.
So it might be.
We can detect contention by looking at runnable, right?
Yeah, that's what is done right now. It's really that on the top chart. When the rate is stay high, it's because we have some contention and the runnable average is above the util average.
Right.
So we are just discarding what was the util average when dequeuing. If I understand on the bottom part, there is the util burst where you're aggregating all the running time as it was only one in order to estimate the util average.
Yes.
So if it was only some time sharing and you have the same runtime, your util burst should still end up at the high value. So I was expecting that to stay high at some point, but start decreasing as soon as the task is really decreasing is runtime.
So the actual problem is the underestimation of util due to contention.
Yeah.
Yes.
Because it wasn't at all clear what he's trying to tell.
That's the point, is that your util average, when you're sharing the CPU, the utilization will decrease because you...
Right, so we can detect this by seeing that runnable is high.
Yes, that's what we are doing. But we have some case, and I think that's what Pierre wants, is that there are some cases where we are still sharing the CPU, but the tasks start to decrease its utilization. And right now, we are not detecting that because we don't know if the decrease of the utilization is because we are still sharing the CPU, or if it's really the task that need to run less.
But we should be able to see that from runnable. If runnable also decreases, the task is actually demanding less.
Maybe, yeah. Yeah, but then there are so many... sometimes it's a bit difficult to see if the decrease of the
It's always
runnable...
difficult. This is trying to reverse something that is...
I'm not seeing, I was expecting...
One other thing maybe is that so I'm resetting the util bursts every time we are unqueuing the task. And if the task is actually running very short amount of time, you can have a high util average value and never really account this in util bursts. So maybe it's this that you...
No, but in this case, you would like...
the renable will be...
Your utility should have to remain high from time to time. I mean, here it really look like if we were not using the util burst and we are removing the renable condition for the utilist, this look like the behavior would have been the same.
I'm not sure I understand we can...
I think he's looking for like parts in your trace where the yellow signal is actually higher than the util average. For instance, like where does your new signal make a difference?
Yeah, so in this signal, not that often. I think it's mainly because we are not sharing. We're not co-scheduled most of the time, actually.
Yeah, but in this case, I mean, if you were not co-scheduled, in this case, the current behavior of utility should have decreased as well. The fact that it's not decreasing means that we are co-scheduled. You see my point? So for me, there is a mismatch between two. Either on the top chart, we should have, if we are not co-scheduled that much, we should have seen the utility dequeuing because we are not co-scheduled. So renable average is the same as util average.
In the top chart, we are not decreasing util S because the delta between the renable and the util average is slightly higher, but it might mean that we have been co-scheduled for 1 millisecond or 2 milliseconds, and it's enough to be higher than the margin, and because of this small amount of time that we are co-scheduled, the util S never decrease anymore. Okay, so now about some limitation of the util average value. So for task, health is measuring at certain amount of time. It's one amount of time. What precise timing? The amount of time that the task received, but can be different to what the task actually needs. But there is still a relation, which is that the time that the task receives is always going to be lower than the time that the task is requiring. Another influence other than task is the niceness of the task. So here, if we have two tasks co-scheduled, okay, the slice length is 8 milliseconds. So if the two tasks have the same weight, we are going to have a sharing of 4 milliseconds, and the utilization of the two tasks is going to be slightly the same. But if there is a different niceness, one task, so here the green task is heavier than the blue task, the green task is going to receive more time from the CPU. And because of this, the utility average is going to grow faster than the blue task. It doesn't mean that the tasks don't have the same size actually, but it just means that we are not giving the opportunity to the blue task to grow. So it's a simplification, but what is limiting in this case is we are bounded by the ratio of the load of the task, so the niceness of the weight of one task, and the rate divided by the sum of the weight, the CPU weight. So the sum of the weight of the task on the CPU. So if the two tasks have the same weight, the util average is going to be bounded by 5 and 12. If the two tasks have different weights, they are going to be bounded by a different value. So for the small task, we are going to have a util average value which cannot grow higher than 113. And for the green task, it's going to be bounded by 911 in this case. So one difference between the util average currently and the util burst is that we are not capped with util burst. We are able to grow higher than this higher bound that I described.
The same for util average. Util average can right now util average whatever the max compute capacity of the CPU can reach the 1024 value.
If we are sharing the run queue, I'm not sure. I was talking about so just to show this example exactly. So if here we have two tasks, A and B, the period of 16 milliseconds, duty cycle of 70 and the same niceness. Here we are following the util average in blue. The util average cannot go higher than around, so it's not super accurate, but it's going to be around 500. Here, task A has a niceness of -10, which means that it has a higher weight. So the util average can go higher. Here, there's a niceness higher, so the weight is less important, and the util average is going to be lower than, so it's going to be around 300. So it means that we are going to be able to have a utilization value anywhere between 0, maybe 1, and the duty cycle of the task. This is for the case where the CPU is almost fully utilized, so almost never idle. So the util average in this case is a lower bound of an accurate estimation of the task. It's an issue because, so not only in EAS, but in this case, we are still some part where we are using the utilization values. For instance, in a task fit CPU, to check that the task is going to fit in one CPU based on utilization values, which is a check based on values that are going to be slightly inaccurate. And in the uclamp max case, so uclamp max is designed to lower the frequency of a CPU for one task. So we are putting ourselves exactly in this scenario where we are not really able to estimate the size of the task. So it's an issue because EAS is also mainly based on power estimation based on utilization values. So
the whole of EAS only works if the tasks do not run more than the CPU time. As soon as you saturate the CPU, EAS goes out the window.
So yes, but in the uclamp max case, not really, because it's a setting that we can. So a specific case where we say the CPU is actually not fully utilized because we are limiting the frequency of the CPU on purpose. So it's okay.
So what problem are you talking about now? Is it still the same problem?
Yeah. It's a question for me?
Yeah, because I can follow what you're talking about. I know.
It's the issue like with the patch we are fighting about, the one in uclamp sum aggregation. Hongyang takes out, where we let heavily uclamp max tasks into the energy model calculation. And then obviously the algorithm is overwhelmed because this task seems to be small, but it's essentially running for a long time. So there is no idle time. Your approach is saying if we run into those things, we let energy-aware scheduling fail, and then we have other things, runnable number of runnable time, or this kind of runnable average thing you do, and then you do still do even though the energy model fails, you do a task placement decision in this path. Before this patch, we were just failing and went to normal capacity-aware scheduling, and I think this is what this is about.
Even in this case, if we have one task which is making a CPU fully utilized, is going to make all the util values of the other task slightly wrong. So we cannot place it as
move that away. I mean, as soon as you see no idle time, you're doing it wrong.
Yes, but even maybe slightly before, because
the runnable signal is the one you want to look at. If that's flatlining at the top, then all the other numbers are wrong.
Yes, yeah, definitely.
But I mean, even in the case of the task that is clocked by uclamp max,
Otherwise you can't fit it into
That's the problem.
we really, I mean, what you would expect to fix with that? I mean, what will be the benefit? So the first thing that the task fit and the average is below the accurate estimation, mainly because, I mean, it's only true if it's co-scheduled. Otherwise, you will get the highest, the normal value. So your point is that if a task is always co-scheduled, that's your point.
Also, if you lower the frequency on purpose, you're going to get an accurate estimation way later, because the faster you run, the faster you will get a good estimation of the task as well. So if you lower the frequency you're running at, it's more likely that you will need to wait a lot more before getting this right estimation.
Yeah, I mean, for tasks that are used with uclamp max, usually it's not. We don't care about performance. I mean, it's something. I mean, we agreed that those tasks just have to run as a background task, but we don't really care about some kind of latency or getting the right utilization value, because the goal is that we never consume too much power because of them. You see my point? So what do you expect? If I understand correctly, you expect to use the utilized.
No, so in this case, I'm not. So this new signal, the util burst, is also not going to get a right estimation of the task. In this case, no signal is going to give a right estimation of the task. It's something that we cannot really identify. So the suggestion is more to say that uclamp max maybe is not a good thing, because with that we are unable to estimate the size of this task.
Yeah, but on the other side, that I mean, is it a real problem? Because we know that those tasks are expected to just consume
so in this case, effectively we are making decision on. We are making decision on utilization values. But in this case, so it's what is in the load balancer. We are in the group imbalance case. We are looking at the load value. In this case, we say that the utilization value is no longer usable. We are using the load value, but in EAS, we are not going to use the load, because it would mean that we would have to do load balancing in EAS in this case. But we are still using the utilization.
Yeah, I'm not sure to get where you want. I mean, because what you're saying is that even in the case of the util burst, in this case you are not able to get the.
There is no proposal of this.
No, this is just, yeah, exactly. This is just some indication of the util average value. It's just to say that in this case, when the CPU is fully utilized, we cannot estimate the task, and we should not put a CPU in that situation.
Okay.
There's no suggestion. I mean, actually, the suggestion would be to remove the contacts.
So on the one hand, the users don't run faster than this. And on the other hand, you're then saturating the CPU.
Yes.
And then you're blaming the kernel.
No, I'm saying that. Yeah, but.
So no, this is the user doing it wrong and he gets kicked to pieces.
But it also means that we are facing some issues to balance tasks in that case because we don't have a right estimation of the task. And this is what Vincent wants to do in a dispatch set, to balance the load, not the load, but balance the load based on the number of tasks per CPU. But in that case, we should actually balance the load based on the real load value, so the weight of the task. Otherwise, you could have two tasks on one CPU with a small weight, and two tasks on a CPU with a high weight, and from the number of when you look at the number of tasks, it's balanced. But when you look at the load of the CPU, it's not balanced actually.
Yeah, but as I mentioned, when you start to say equal max equal 1 for a task, it's a way to say I don't need any kind of performance. So
you could say it's equal to 100 or 200. It would still the example will still work. So.
Yeah, but how to accommodate ucount max and niceness is not
possible, I think. But
because on some parts you say, I don't need a lot of performance. I don't care about the performance, and on the other side you say, I want to keep my CPU shape.
So as we discussed earlier, you can say, I don't need to run really fast. And I want to have a niceness of 10, but a second task can say the same thing and say I want a niceness of 15. And in this case, the two tasks don't actually want to run much, but one task would like to run slightly more than the other. And in this case, we cannot balance these two tasks. So we are somehow breaking a bit the niceness.
Yeah, but
Yes.
But on the other hand, if you run with a task which is not long,
so it's it's not the initial
okay.
issue.
So I'm not sure where you want to go with this. Then it's just to say we have a problem, or
yes, more or less. Well, yeah. So I don't have to solve this.
and so I'm not sure about the conclusion for the util burst. Is it useful as solving something, or you just show that that's the point? I'm not sure, because what you're showing there is that finally it doesn't solve this case.
No, so this was a new topic. So util burst is more or less finished in the presentation. It's just to discuss about the limitation of the util average value. So it has nothing to do with the util burst. So just to finish quickly, so there is also time scaling and frequency invariance, which means that we are able to estimate the task independently of the frequency and on the size of the CPU we are running on. So if we have one CPU which is running, which has a capacity of 512, what we are doing is that we are compacting the time contribution when we are computing the util average value. It means that in some cases, if the CPU has a really low capacity, it will take much more time to take into account the contribution, because we are taking into account a contribution every 1 millisecond. if the CPU is really low, it means that it can run 8 milliseconds without having the util average signal updated, which is so 2 ticks. So it's can be a bit.
So just util average is accounting the cycle that you have really used. That's really the goal. It's how much of CPU you have effectively used.
Yeah, right.
So that, I mean, that's a way to account the number of CPU cycles that you have. So yes, when you are running at a low frequency, the cycles are longer, so it will take more time. But we really have to keep that in mind. Util average, it's really about an average usage of CPU cycle.
Yeah.
And with all the drawback that we have there, that's why we have the UTLS, for example, as a way to keep in mind what was the EAS utilization.
Yes.
But this is only good for periodic tasks, util-S. And just to put this into perspective, that's why Case came up with this patch we discussed before. That's exactly the underlying problem for him on his small CPUs, where this can happen.
I think Dietmar is talking about the fact that the wall clock time can be, you are going to wait longer because you are scaling the contribution with the CPU capacity. So it can, if the task spawns a little CPU, it will take a short time.
Yeah, but then we are speaking about two things. I think that what we have to keep in mind. Here, we are accounting the cycle that we use. And right now, we have a linear mapping between that and which compute capacity or OPP or CPU should be used. And that's probably where is the problem, because that's, I mean, if you're running slowly, yes, we will take some time to increase the util average. Now, it's just that we have these linear things. Maybe it's not the right things, and that's something I discussed with Case. And maybe we should, we can use something different. We can use a PID if you want to increase fast, and so on. But then there is another problem with EAS that we need to estimate what will be the OPP that has been selected in order to estimate what will be the energy delta if I put that task on CPU A and CPU B. With a linear mapping between capacity or utilization and compute capacity, it's quite straightforward. If we start to add something where you will increase faster, then it's quite difficult to estimate what will be the OPP, because the OPP might depend about the previous behavior. If you are increasing fast, that's something we have to keep in mind.
Because recently we have all those nice EAS patch sets, and there's very little review among all the stakeholders. If Case sends out this patch set, then we should discuss all of this.
So there is, it's just that, I think what we are using this linear mapping just because it's quite easy to estimate the OPP, estimate the cost, estimate the energy impact. Now, I mean, we can do whatever we want.
So I was not initially talking about that. It was just to, just to come back to this. So what we could do is just increase the granularity of the PET staircase estimation. So we could have, instead of one value every 1 millisecond, if we had one value every 256 microseconds, it would help update this util average value more often, but the ramp up would be the same actually.
Yes.
And that's all I wanted to say.
So do you expect, I mean, if we were in this case, for example, let's say that, for example, right now we have 10, 24 microseconds, which is not, I mean, some scaled microseconds, because does it would be helpful if we should add more update? I mean, let's say we are running 4 times slower. In this case, it's each and every 256 microseconds.
So it's supposed to be more accurate, but when testing it, I didn't see any improvements.
Yeah, because we are speaking about one millisecond. So the step is not that huge at the end. I mean, we are not doubling capacity.
Yeah, exactly.
So that.
So it was the conclusion of this. And so summary. So util burst would be a way to have a good estimation of tasks when they are co-scheduled. And so far there is no improvement in score, but should work maybe, I guess. And the granularity is supposed to improve the palette accuracy. Don't have any result as well. but I assume that there is little to gain actually. So yeah. So if there are any questions, otherwise I think I'm just.
I think the real problem for us, they come when we introduce those little things and we just back it up with a performance test case, speedometer, and then I deliver the energy model, data later. So then we might introduce those things where somebody else figures out later, okay, now we are more agile, but we burn more energy.
Yeah.
Right? So we have to find a way to only let this happen, but this is very hard because we don't have a set of test cases you can run with energy numbers and they say it's overall it's better.
Yeah, or even a platform where you are.
Exactly. So this is we should be more careful to introduce all those small.
So typically the patch that I'm working on, I'm testing that on Pixel 6 with the AOSP, but clearly I'm using the plain AOSP. Mm-hmm. So I'm not sure that I have all the features that other hybrid devices are using.
I mean, if we let those things in, then it has to be clear to us that they might regress.
Yeah.
Because probably like the phone manufacturers or the Android guys will figure this out 1 year later.
To be honest, so yes, it can regress. If it regress, a normal setup, but then I would say if it regress because of the hook, I mean, it's not really a problem for me. If it's regress because the behavior changed from a global point of view, yes, it's a problem. But if it's because their hook finally was trying to fix already that, and there is a conflict.
But you are testing with AOSP with all the hooks in place.
I don't have any hooks.
Okay, so it's mainline.
It's really mainline.
What they call mainline.
Yeah. And I think I don't have ADPF enabled. I don't have C-Group and Uhldingen used by AOSP.
Yeah. So thank you for listening.